Hello and welcome to Brunei Math Club. In this video, we study square matrices, which are n by n matrices, and compare the set of square matrices of a fixed order with the set of integers, and see both of these sets share the same structure called the ring. Okay, let's start. So, a square matrix is a matrix that have the same number of rows and columns. That means they are n by n matrix for some integer n. We have been studying various operations on matrices. Here in particular we consider matrix addition and matrix multiplication and see how these matrices, square matrices, behave under these operations. Before proceeding further, let us define a set Mn, which is the set of all n by n square matrices. And let us summarize the properties of this set. First, if A, B, C are elements of this set, that means A, B, C are all n by n matrices, then we have this associativity of addition. A plus B plus C, brackets here, is equal to A plus B plus C. So this is associativity of addition. And the second property of addition is the commutativity. That is A plus B is equal to B plus A. So we can swap the order of addition. And the third property, there exists the zero matrix, we denote it by O in this set, such that A plus O, zero matrix, is equal to O plus A, because of commutativity, is equal to A. So adding the zero matrix doesn't change the original matrix. Well, maybe we should put for all A in M here. And next, for all elements in this set of square matrices, there exists a unique element called negative A, such that A plus negative A is equal to negative A plus A is equal to the zero matrix. So this negative A, well, we have defined negative A as in terms of the scale-up multiplication by negative 1 times A. But here, we don't assume this. We just say for any elements, element A, there exists some special element such that if we add this element to the original element, then the result is 0. Okay, that is called the additive inverse of A. If you have studied some group theory, you can see that the set of square matrices satisfying this associativity, commutativity, and the existence of the zero element and the existence of additive inverse, it's called additive group or abelian group or commutative group. Let's say abelian group under addition. So these are the properties of addition. And what about multiplication? For multiplication, we have also associativity. So A times BC is equal to AB times C. So multiplication is associative. And for matrices, commutativity doesn't hold for multiplication, but we have a special element called the identity matrix. So this is identity matrix, such that A times I is equal to I times A is equal to A. So multiplying a matrix by the identity matrix doesn't change the original matrix. So any set with these properties, the associativity and the existence of some identity element, is called a monoid. So the set of square matrices is a monoid under multiplication. Now let us combine the properties of addition and multiplication. We have something like this: A times B plus C. Of course, we add B and C first, then multiply by A from the left. This is equal to AB plus AC. And similarly, we have A plus B times C equals to AC plus BC. So this is called the distributive law. So we know that addition is associative and it's commutative, and there is a zero element, and there is a additive inverse for each element, and multiplication is associative, and there exists some special element called identity, and the multiplication is distributive over addition from either left or right. So the set Mn, the set of all square matrices of order n, together with addition and multiplication, such a structure is called a ring. So this set is one example of the ring. In mathematics, we find many such structures other than square matrices. Of course, you know the set of integers satisfies all these properties, right? Additions of integers is associative and commutative, and there is an integer called zero integer, and for each integer there is negative of that integer, which satisfies this property. So the set of integers is an abelian group under addition, and integer multiplication is associative, and there is a special element, one integer, such that this property holds. And integer multiplication and addition satisfy these distributive laws. So the set of integers is also a ring. So we can deal with the set of integers and the set of square matrices in the same manner as far as these 8 axioms are concerned. If you are interested in more general theory of rings, then have a look at another playlist I have on this channel. As much as there are commonalities between integers and square matrices, there are significant differences. For example, for integers a and b, we have the commutative law. A times b is always equal to b times a, which doesn't hold for matrices. But if you are careful enough, then your knowledge of integers may help to understand the properties of matrices. Okay, that's all for this video. See you next time. Bye. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.